This talk is about Network Data Analytics Service, which is the 3GPP framework for enabling artificial intelligence and machine learning in 5G network core. We will be covering only the concept of the infrastructure required for this framework. I will not be discussing any specific machine learning use case in this talk. Before going deep into the 3GPP specific framework, we will have a quick look into the state of machine learning system in generic. As we all know, the core of any ML system is of course the ML code. But there is a lot of extra work required to productize this code. Till few years back, there were very minimal tool support available for building such a system. In 2015, a few Google engineers written a paper where they highlighted this issue. They stated that the actual ML code is the tiniest part of the entire system. This diagram is from that paper where you can see the ML code is the smallest block of all. Later, this paper became an inspiration for building tools to solve this problem. Today, this area is maturing into a practice or a culture, which is now called MLOps, which stands for Machine Learning Operations. The NWDAF, which we discuss in this talk, can be considered as an extension of MLOps in network system. When it comes to 5G, the system is expected to be extremely AI capable. But to efficiently introduce AI to network system, ideally the analytics should be separated out because the requirement of a ML system differ from other parts of the system. 3GPP has defined a framework for this, which named NWDAF or Network Data Analytics function. Along with other supporting functions, it aimed to provide a standard interface for data analytics on 5G systems. NWDAF was introduced in release 15, but did not see much adoption. The main reason I believe for this slow growth is first, it could be the unavailability of data. 5G deployment are just taking off, not much data out there, and even if you can build some use cases with 4G data, think who owns these data? The telecom providers, right? Unless you have access to this telecom data, it is very difficult to come up with real ML use cases. Second reason for lack of adoption of NWDAF is the definition of NWDAF in 3GPP standard was very minimal and was not good enough to build a system. But this situation has changed in release 17 and has necessary standardization for all required functions for a complete system. Now, before going to the platform part, let us understand in high level what a NWDAF use case consists of, because we need to know the problem to rightly solve it. A typical use case will consist of one or more machine learning models. Building a machine learning model is an iterative process, and data scientist will experiment the models. Basically, he or she will try out different algorithms, tuning parameters, etc. on different data set. He compares the result and finally decide on a model which can be productized. But even after the deployment, it needs continuous monitoring and retraining. A serious use case might be a combination of many ML models, and there will be an overlap of data that is required by the models. So, and a use case might be a base for another use case. In essence, if you think about a complete system in a longer term view, it might have tens or hundreds of use cases and maybe hundreds of models, and the platform have to manage all of them. Now let's see how NWDAF differ from NF in general. First is the requirement of retraining. When we consider an NF, once we implement and deploy it, we don't expect its behavior to change. It might change, it might have bugs, or we may add new features, but what we already written will behave same way for the same input. So if we do a trial run of NFs and deploy it for actual uses, it will behave same. Maybe load related issues might be there, but otherwise it will behave same. But an ML system is different. It is tightly coupled to the data it was trained. So if we train our models in the trial runs and deploy it in actual environment, it might not work in the same way as we expect. This is because the data pattern might have changed from the trial runs to actual environment. This is called data drift. So when a data drift happens, ML models will perform badly, which is called the model decay. In such cases, the model need to learn the new data. So this is a continuous process in the lifetime of ML model, and sometimes even retraining won't help. In that case, model need to be redesigned. The second difference is the requirement of historical data. If you consider an NF, you know it just need the current state of the machine. It changes the state from one to another based on some internal or external trigger. But a machine learning system analyzes historical data to derive the future expected values, or it might analyze the recent states of entire system to check whether there is any anomaly or not. So this requirement of historical data is important for the design of NWDAF platform. Now we will look into the 3GPP specification. So we will start with this base function NWDAF. Basically, it is a thin API layer that provides a standard interface for other network elements to get analytics. The consumer can be an NF for AAM or AF or NEF, any other network element. So consumer can request or subscribe to analytics from NWDAF. Each NWDAF will be identified by an analytics ID and an area of interest. Area of interest is optional. So single NWDAF can provide multiple IDs also. We will now see some important concepts of NWDAF to get an overall idea of functionalities of it. The first, we have already seen this is the requirement of historical data. We'll just take one example. So let's assume that this ML model require 24 hours of measurement, some measurement, and the data will be provided by say one NF or OAM, and the NF can give only current measurement. So now it is NWDAF responsibility to collect this data and keep it, and when a request come to send this 24 hours of data to model and get the analytics back. So this, and you have to think that there will be many NWDAFs in and many models there, and we have seen that there could be overlap of data, and if you doesn't manage your data well, you could have a lot of duplicate efforts for collecting the data and also for storing the data. Next concept, area of interest, is not very specific to NWDAF. It applies to other network functions also. The area of interest is geographical location that NF belongs to. Each NWDAF instance may represent one area of interest, or it may represent a larger area which contains multiple area of interest. Note that since UE is mobile, it may move from one area of interest to another. Another concept that is important to discuss is aggregation. There are different types of aggregation that NWDAF can do. So one type is based on area of interest. We have seen that area of interest can have separate NWDAF for each. We have seen that each area of interest can have separate NWDAF instances. Now in some cases, analytic consumer may require a larger area. So like here, this consumer require 3 area of interest. So some NWDAF can act as an aggregator. In this case, this third NWDAF is the aggregator, which collects analytics from other NWDAFs and send a single aggregator result to the consumer. Another type of aggregation is analytic aggregation. We have seen that a use case can be made up of another use case. So in such cases, like in this case, you can like this AID3, the analytics ID3 is made up of other AID1 and AID2. You probably add some logic there, how these are related, and then you get a new use case. So this kind of aggregation is called analytics aggregation. So another feature of NWDAF is analytic subscription transfer. So one NWDAF can transfer subscription to another NWDAF. So for example, assume NWDAF is providing some analytics related to a UE. So now the consumer need analytics of this UE, and since UE belongs to an area of interest, this first NWDAF will be providing the analytics of this particular UI. Now this NWDAF is providing the analytics for this consumer. While doing that, assume that this UE is moved to another area of interest. Now the responsibility of providing the analytics now for this UE is now this second NWDAFs. So in such cases, the standard provides a way to transfer the subscription itself. So consumer doesn't have to do anything. He doesn't have to stop from here and move to there. Basically, NWDAF itself can transfer that subscription. The consumer will continue to get the analytics without interruption. So another use of analytics subscription is during graceful shutdown of load balancing. If there are multiple instances of same NWDAF or HAR load balancing, this kind of transfer is useful. So now before going more into the platform part of NWDAF, let's go back to the diagram we saw in the first slide. How it will look if we redraw that for NWDAF. So now this is just my view of it. So the platform that required for NWDAF to be functional require everything we saw there. In addition to that, we have to deal with this 3GPP standardization. Specifically for data collection and serving, the standardization is important. Now we will look into all the functions that defined by 3GPP to build a complete system for data analytics. So there are 5 major functions. So NWDAF is divided into 2 functions, ANLF and MTLF. So ANLF is analytical logical function, which is the core of a use case. So this part will be written by probably an MLOps engineer for each use case. And second is model training logical function. This is the provisioning and training part of models. So you can have this ANLF and MTLF together. So basically you can bundle your model and use case logic together. In that case it will be called NWDAF. So the third is DCCF, data collection and coordination function. So I would say this is the core of the platform. It's the data management layer. So we'll soon see how it works. So then fourth is ADR for analytics data repository function. So this is the storage layer. It is an adapter layer for storage. Basically you can have different databases underlying, but this layer gives a standard interface for that. So next is messaging framework adapter function. Since this system involves very heavy data transfer, it is better to have a messaging framework. MFAF is adapter layer for your messaging framework. Underlying you can use any common frameworks of your choice like Kafka, RabbitMQ, etc. Instead of bullet points on each service, let's look at one of the flow which involves all the services. All services has other responsibilities. It is difficult to look at everything. So I hope this discussion will help to get a generic idea. So let's start with NF, which is an analytic consumer. So it needs some analytics from one of the NWDAF. So it can request that to send that request to NWDAF itself, or it can send that to DCCF. So let's assume that it sends to DCCF. So now DCCF will forward that request to the NWDAF, ANLF, and so now this NWDAF require ANLF require two information. One is where is the model endpoint, or if there are multiple models, where are the model endpoints, and the second is the data. So it need to collect the data which is needed by the model. So it requests MTLF for the model endpoint. So MTLF is responsible for training the model, deploying the model, and all models may not require, some could be pre-trained. So in that case it can just deploy that. So and some maybe, it may have identified some model decay and you need to retrain that. So in that case it basically retrain and deploy that. So at the end what it gives is a endpoint of a model microservice. So that model endpoint it will pass to the ANLF, and now ANLF require the data. So it requires DCCF for that data, whatever it requires. DCCF check whether required data is already available. Otherwise it need to start a new data transfer between NF and ADRF. So DCCF initiate a transfer. When data is not available, especially when NWDAF require longer period of data, DCCF will reply that data is not available, and NWDAF will respond to the consumer with an analytics but indicating that it has zero confidence on the prediction. So data transfer will happen between NF, ADRF and messaging framework, and finally when required data is ready it will send back to the NWDAF. Now NWDAF will request analytics from model, and model microservice will reply with the required analytics. Finally ANLF will construct the response with this analytics and send it back to the consumer. So now let's look this at a system design point of view. Again, a complete design discussion will be overload for this talk, so I'll be just start the thought process. Let's see one scenario which we may have to handle. So let's assume that one of the NWDAF is requesting some data from DCCF. So this require some data from say NF1, NF2, and DCCF requested data transfer, and data transfer happens, and finally NWDAF will get the data. DCCF is just an initiator. It just start the data transfer, and all other actual transfer will happen between all these other components. So now assume that this DCCF crashed. So another service will come up, but now assume that another NWDAF is requesting for a data and same data. So in this case what our expectation is that because already the data is there in ADRF, another data transfer should not be initiated. This should be transferred. That data which already have should be transferred back, and that is the responsibility of DCCF. So, but in this case, DCCF doesn't know that already a data transfer has happened. So, because the one who started has died. So now then there is a duplicate effort which happens, which because the second DCCF also will start a data transfer. Basically, that means that there is a DB required outside, right? So maybe it could be IDRF itself, but for discussion, let's take it as an DB, any DB. So now that gives more problems, right? When you a distributor system become stateful, we are introducing more problems. So see one more problem. So now say this we have multiple instances of same DCCF for load balancing. So now let's say the first NWDAF requested same data which we already discussed, then this time and DCCF will look into database, but and now it got that there is no transfer happened, so it can start a data transfer. But before that happens, that actual data transfer happens and DCCF updates the DB, there is a time gap. In that time gap, another request can come, right? So and it could check when the DCF2 checking the DB again, it's empty because DCF1 has not updated it yet. There could possible, like you can have logs, but logs will be again more problems, right? So now again that same duplication of effort will come. So that means that we probably have to introduce some coordination service. But basically I'm saying the system is becoming complex and bulky. So the choices you make here for each components will decide how your system will do in the long term. Everything will work initially, but you will hit the real issues only when you try to scale in production. So we have to be very careful while designing the system. The system is very complex. Okay, so now we'll just see the data collection part of it. So now we have seen that data collection is the most important responsibility of the platform. So data collection for analytics in the NWDAF point of view can be at say 3 levels. The first is the first stage. When the data scientist or ML engineer build the model, he require a longer period of time data. So and it should be accessible. It should not be on edge or network core. It should be inaccessible for him. So ideally it should be on cloud. So this part of which require the longer term, it's normally, we can say this for ML pipeline, which is we basically use for analysis and training, basically the experiment part of it, and it should be stored in data warehouse or a data lake. And second part is like online training. So online training could be done on a smaller set of data, so probably days of data, and that could come from an ADRF. So the last is ANLF, or that is required for an inference, the model inference, and that could come from ADRF, ideally from ADRF, or it can come from NF or OAM if it's support the required number of data required. It might not be just current data, it will be some historic data. So if it can provide it, it can be directly collected from NF or OAM. So please note that this time period depends on use case. Sometimes for some use case, maybe just days of data could be enough for ML pipeline training. So now to understand MTLP more, we need to know model serving. So models basically contains code and train parameters. But for application to use it, we need to convert that to a microservice. So basically it gives some endpoints. So this part which converts a model to a microservice is called, that infrastructure is called model serving. So there are different frameworks available for this. We'll look into them. So before that, for MTLP, what could be the input format? So first is ML code itself. So if a model MTLP is doing the model training, then it might require the actual ML code that probably written in Python or R or something. So the second case is saved models. So this is most popular way of sharing the data to models for data model serving. So it basically include both code and trained parameters. It is basically a pre-trained model, so it's already trained, so both code and trained parameters will be already in that saved model. The third one is we can actually pass the microservices of some image you can create, and that images of you can pass. So now looking at different serving softwares, there are many frameworks available. The most popular could be the TF serving, TensorFlow's serving infrastructure. So because of TensorFlow's popularity, this is also very popular, and it's very simple to use also. And the second is TorchServe. So this is PyTorch serving model, serving infra. And third is Titan inference serving. This is from NVIDIA. So this has some optimization for NVIDIA GPUs, and it supports many different frameworks like TensorFlow, PyTorch. So this is another popular serving model. Another software that worth mentioning is Akumos AI. This is effectively a serving and a cataloging software. This is a project started by AT&T. Because of this lineage, this is well talked about in telecom industry. Another important concept that we need to understand is feedback loop. ML model, we have seen that ML model performance can decay over time. So this will have a very high impact on the system negatively. So instead of improving the system, it could degrade the entire overall system. So a continuous self-monitoring of models is required. So we have seen what data drift is. So when there is a shift of pattern in data, we basically call it data drift, and retraining with the newer data is required, and this can be managed by both MTLP or outside of the edge core, basically on the cloud. So and redesign of model may be required in certain cases. So sometimes even you retrained many times, the model performance may not improve. That means you probably require a redesign of ML model. So now the MTLP has to send a trigger in such cases to the outside world, probably to the model management layer, when a retraining is no more effective. So now we'll look at the ML pipeline NWDAF interaction. So when I say ML pipeline, it basically means that the layer which the data scientist or ML engineer will use to train, experiment, all those kind of stuff. So in a broader sense, everything we saw now also part of the pipeline, but for this discussion purpose, we will just take that as the ML pipeline. So Now, one thing to note is that this is outside the scope of 3GPP. The pre-trained model is outside the scope of 3GPP standard. We can see that to connect this cloud part to the NWDAF part, we need three interfaces basically, so which are marked in blue here. So the first one is the model deploy. I mean, it's we already seen that by the different formats to deploy and all. So this that model which the data scientist has been created, or ML engineer has created, designed and created, has to be pushed to the MTLF. That we need an interface. Second is the model feedback. So when a trigger is need to be sent, that need an interface. So these are the two interfaces MTLF side we required. And third is the data for longer term. This is actually very important. This is needed from day one, because without data you cannot design a machine learning use case. So basically this data from ADR for network functions or network elements has to be pulled to the cloud layer. So these are the three interfaces which we require. And when it comes to the pipeline, as we said, data scientists or ML engineer use this to do experiments with algorithm and data. For initial analysis, they require data for longer term and should be easily accessible, hence they should be available in cloud. For ML pipeline part, there are many solutions, managed solution from all major cloud providers, and also the products which you can deploy and use. Now coming to data storage, there are majorly two types: data warehouse and data lakes. In data warehouse, you can convert your structured or unstructured data to a queryable format, but in data lakes you can dump them in original format, text, JSON, binary, whatever it is. Although there was a time when it is considered data warehouse technology is dying, innovations around it has made it a strong comeback now, this time but in SAS format. Some examples are Google BigQuery, AWS Redshift, and Snowflake. So Snowflake growth figures and historic IPO is an indication where this technology is heading. So now the ETL is a step where data is extracted and transformed and loaded to the storage. In some cases, especially when the endpoint is data lake, data will be loaded without transformation. So and transformation is done only when it is needed. So this is called ELT, extract, load, transform. And when it comes to collecting data from source, traditionally it is done in batch process. For example, we can collect data from ADRF and send out in batches. So ADRF will collect all the data, as we saw, like all the DCCF involves in that, and in batches we can send out to the cloud. But today event streaming is the trend. So and we can see that actually the streaming gel well with other components of NWDAF. So we should consider event streaming also for this purpose. Now, which data to be uploaded is very complex subject. The way ML experience happens, it is very difficult to know in advance which all data is required for the experiments. But uploading all data can become unnecessary use of resources like bandwidth or CPU. Also, data protection laws of geographical area where the edge is located also comes into picture, like GDPR. So this component should be designed very carefully, and it's actually a very complex component to be designed. So now when you think about the distributed system platform that NWDAF or other functions will be deployed, like Kubernetes, networking, etc., Since all services we discuss are network function, those are to be dealt in a similar way like any other NF by underlying platform. So we need to design the NWDAF platform with minimal assumptions about underlying ecosystem, but underlying ecosystem should be designed in a way that NWDAF also can be accommodated. Now for a completion point of view, I will just give an introduction to SDK that is required to make the life easy for a user. Here user is an MLOps engineer or an ML engineer. Let's see what are the basic logic in an ANLF, for example. First, it need to register to the system. So now, except for these two parameters, analytical ID and area of interest, all the logic of registration is same for all NWDAF. Now for like that, I mean, for the use case logic, we need to get the model endpoint from NWDAF and MTLP. Using that endpoint, we need to get the prediction and then the actual aggregation logic. So except this aggregation logic, everything else is reusable code. And finally, we need to notify to DCCF and send the data. Now, so you can see that most of this logic is reusable, and we can build a library around this. So which helps the ML engineer who will be coding the use case to write a NWDAF with few lines of code. Also think about a situation if we give the responsibility of writing a code for the stuff like analytical subscriptions transferred to the application developer. So that could be really dangerous, right? So these need to be taken care by SDK or the platform. So now to conclude the design, let's look at the high level view of NWDAF platform. So which we already seen all the components. So first we'll have the MTLF framework or SDK and ANLF SDK, then DCCF, which is probably the core of the platform, and all your NWDAFs or ANLFs and MT and models will be running here. We will have some messaging framework like Kafka, and over that, to provide a standard interface, we'll have messaging framework adapter function. Then we'll have a storage, something like InfluxDB, because this could be a time series data. So then we have an adapter layer for that. Then which all this will be running on our distributed system platform. So now before concluding, we will have a quick look at some interesting difference between NWDAF and RIC. So this will make us understand NWDAF more. RIC is the RAN intelligent controller. As we see, the 3GPP standard has classified the components based on functionality, like data collection, storage, analytical, logic, etc. But the major theme followed in RIC is latency based. It is divided into 3 layers or loops, as they call it: real time, near real time, and non-real time. So although the NWDAF provide a way to achieve the latency requirements, but that's not the major theme here. Another difference is NWDAF is very specific to analytics. It doesn't deal with application logic like a closed loop. Other functions can use NWDAF service to build a closed loop, but that is outside of NWDAF. But in RIC, closed loop application can be written as XApps or RApps. Another important difference is, as mentioned, NWDAF is only for analytics. So no policy management is part of it. policy control function or PCF can use analytics from NWDAF for decision making, but that is not taken care by NWDAF. But in RIG, there is a tight integration of policy management. So finally, we'll conclude the talk with a look at the release timeline. Architecture changes for release 17 is mostly in. You can see that is Q3 2021, and we can assume there won't be any changes in architecture now. So the stage 3 freeze is on Q2 22, and protocol etc are Q3 22. But we can expect there will be needed definition to start an implementation of platform by Q1 or Q2 2022. So thanks for listening. If you like to connect with me, please follow my Twitter handle, which is shown here. Thank you.